Introduction to Anova. So Anova stands for Analysis of Variance. So this is going to be actually a test about the difference in the means, but we're going to look at the variability within the groups in order to get to our conclusion. So we have this fictitious data set of lamb weight gain on 3 different diets over a 2-week period. You can see that diet 1 has 3 observations. Over here in the data table, you see the 3 observations, and over here on the plot, you see those 3 observations plotted. Diet 2 has 5 observations, and diet 3 has 4. So looking at the plot, you could already start to make some conclusions for yourself, but of course we have to think statistically. So what is the question of interest here? What would you want to know if you were looking at this data set? Well, if I was looking at this data set, I'd want to know, I would think that the farmer wants to know which diet works the best. So our research question would be, which diet works the best? So how do we analyze this data? Well, we have independent samples, so why not use independent samples t-tests? Well, using the t-distribution to make more than one comparison of a pair of independent samples drives up the chance for an error. So remember, the type 1 error rate, which is the probability of going with the alternative when we shouldn't of a t-test, is the significance level alpha. The lamb weight data is comprised of 3 independent samples. So how many pairwise comparisons can we make? Well, we can have diet 1 versus diet 2. We can have diet 2 versus diet 3. And we can have diet 1 versus diet 3. So that's 3 pairwise comparisons, which would mean we'd have to do 3 independent samples t-tests. So we could make a type 1 error on any one of these comparisons. So let's look at what happens to the probability of at least one type 1 error when making all 3 multiple comparisons. So let's let E denote an error, and let's let C denote being correct, so not making an error. We made the correct decision. We're going to assume that alpha is 0.05 and that we're making 3 comparisons. And if this was the case, and we want to know the probability of making at least one type 1 error, what is the probability of making at least one type 1 error? Well, the complement of that is making no errors, right? So this is going to equal the 1 minus the probability of no errors, which means that they're all correct. And can we compute that probability? Well, that's 1 minus the probability that we're correct on the first, and we're correct on the second, and we're correct on the third. And of course, this is assuming that we have independence, which is a very strong assumption. It's probably not met, but if they were independent, that would be 1 minus the probability of being correct on the first times being correct on the second times the probability of being correct on the third. So if we assume that independence holds, which is fine for example's sake, then it's 1 minus the probability of being correct on the first. Now, what's the probability of making a type 1 error? 0.05. So what's the probability of being correct in that way? 0.95. So the probability of being correct on the first is 0.95. The probability of being correct on the second is 0.95, and the third is 0.95. So it's 1 minus 0.95 to the third, which ends up being 0.14. So with just 3 pairwise comparisons, the chance of making at least type 1 error is 14%, which is really high. So you can imagine what happens when we get even more pairwise comparisons. So we're going to talk a little bit more on what to do about this error rate later, but for now, we're going to introduce what's called the Anova test. So a one-way analysis of variance, or just Anova, which is what everyone calls it, is a hypothesis testing procedure that uses the following hypotheses. It's going to test that the mean for the population from the first group equals the mean for the population for the second group, all the way until you exhaust all of your groups, so that all the means are equal. And the alternative is that at least one is different. So notice that we can't do a directional alternative hypothesis unless we only have 2 means, and then it would just be the t-test. And it turns out that the Anova p-value is equivalent to the t-test when you only have 2 samples. So what do we mean when we say one-way Anova? The term one-way refers to the fact that there's only one variable defining the groups. In our example, this is diet. If we had 2 categorical variables defining what's going on, we might have diet and, I don't know, outdoor time for the lambs, or I don't think you exercise them, but I would say outdoor time, maybe different levels of outdoor time, and diet, then it would be a 2-way Anova. We only have 1 categorical variable predicting our response, so it's a 1-way Anova. So now we have to get some notation out of the way. Capital I is going to denote the number of groups. Lowercase I is going to denote the ith group, and lowercase j is going to denote the jth observation within whatever group we're in. So y sub ij, talking about this one right here, if it was y sub 1, 2, it denotes the second observation in the first group. So y sub ij, I is 1, first group, 2 is j, second group. N sub I is the sample size for the ith group. Y bar I is the sample mean for the ith group. N dot is going to denote the total sample size across all groups. And then y bar bar, we really could have called it y bar dot, is the total sample mean combining the data across all the groups. So now we're going to mention something that we talked about before when we talked about regression, and this is the sums of squares. So we're going to look at 3 different sums of squares, just like we did in regression. Remember, in regression, we had the sum squares that was attributable to the regression, the sum square that was attributable to the error that was not attributable to the regression, and then the sum squared total. So we have the same 3 components when we think about an Anova. All right, so the sum squared within is the within group variability. That is the natural variability within a group. So the natural variability attributed to just weight gain in general. So within a group, the way we're looking at that is yij minus y bar I, which is the jth observation in the ith group, minus the sample mean for the ith group squared, and then summed over all the groups and all the observations. So here we're looking at the individual observations and their distance from the sample mean of the group that they belong in. So this is our sum squared within. So we take those deviations, square them, and add them up just like we've done before. Now the degrees of freedom for the within group variability is going to be the total sample size n dot minus I, the number of treatment groups. So I should have used a different font for the I, but that's n dot minus I. And then the mean squared within, this ms is mean square. A mean square is a sum square divided by its degrees of freedom. So the mean squared within is the sum squared that we just calculated divided by the degrees of freedom for within. Sum squared between is looking at variability from a different standpoint. It's looking at the distance of a sample mean for a group to the total grand mean across all the groups. So the sum squared within was looking at the variability of each observation around their own sample mean, right? The sum squared between is looking at the variability from each sample mean to the overall mean. So sum squared between looks at how the groups are shifted from each other. Sum squared within just asks how those observations are shifted from their sample mean within a group. And the degrees of freedom for between is the number of groups minus 1. Because we're just making, we have 3 sample means, right? We're comparing the sample mean for the first group to the total mean, sample mean for the second group to the total mean, sample mean for the third group to the total mean, in our case. And so the degrees of freedom is, again, shifted by 1. So it's the number of treatment groups I minus 1. And again, the mean square is the sum squares divided by the degrees of freedom. So the mean squared for between the groups, and that's how far the groups are shifted from each other, is because we're looking at the sample means compared to the grand mean, is the sum squared divided by its degrees of freedom, so sum squared between divided by degrees of freedom between. And the last one is the sum squared total. And the sum squared total, again, is the same thing we thought of in regression. It's the distance from the individual observations all the way to the grand mean, squared and added up, over all the observations and all the treatment groups. And the degrees of freedom for this one is n dot minus 1. So the total sample size minus 1. And again, the mean squared is the sum squared divided by its degrees of freedom. So the mean squared total is the sum squared total divided by the degrees of freedom total. All right, so consider the deviation from an observation to the overall mean written in the following way. If I look at an individual observation, which is Yij, to the grand mean, which is Y bar bar, I could rewrite it like I did on the right. I still have my Yij minus my Y bar bar, but all I've done is I've subtracted a Yi and I've added a Yi. So notice that the left side is at the heart of the sum squared total. If I go back up here and look at the sum squared total, that is at the heart of the calculation when I calculate that sum squared total. So that Yij minus Y bar bar is the left side. And the right side has the analogous pieces of the sum squared within and the sum squared between. So notice that we have the Yij to the Y bar I and the Y bar I to the Y bar bar, which is our sum squared within and sum squared between. So it actually works out the same way it did with regression, that when you sum all these individually, square them and sum them up individually to get the sum squared total, sum squared within, and sum squared between, that addition property still holds. So this is the heart of how we calculated our R squared in regression. We took the amount of the variability that was attributed to the regression divided by the total variability, the sum squared total. So we're going to do the same thing with an analysis of variance. It's centered around the idea of breaking down the total variation of the observations from their grand mean into the two pieces, the variation within groups, which is the error variation, and the variation between groups, which is the treatment variation. So think about it for a second. If you look at the scatter plot that we started with, there's within group variability. So there's that variability in diet 1, that variability in diet 2, and that variability in diet 3. And then there's the between group variability. So the within group variability is the natural variability in weight gain that lambs exhibit no matter what diet they're given. The between group variability is the one that we're looking for, right, in our research hypothesis. It looks like diet 2's mean might be shifted up a little bit from the other two. So that between group variability, which one has a mean that's different from the others, is what we're trying to get at with the ANOVA, or which ones are different from the others. And that's the game we're going to play to do the Anova test. So we're going to use a distribution called the F distribution to calculate our p-value for the ANOVA. The F statistic, the test statistic that we're going to use, is that mean squared between, so that shift in the means of the groups, right? The between group variability is looking at diet 1 versus diet 2 versus diet 3 and seeing how those groups are shifted from each other, to the mean squared within. So it's the ratio of the variability that we think is attributed to the treatments to the natural variability within each group that's already exhibited with lamb weight gains. So if the data indicates large differences in group means compared to each other relative to the variability within groups, then your F statistic is going to be large. Big values of F indicate evidence against the null hypothesis. So if the group means were the same, the variability between them should not be larger than the natural variation of the data within each group. The F distribution has degrees of freedom for the numerator, between, and the denominator, within. And so we say that our F statistic is distributed as an F with nu 1 and nu 2 degrees of freedom. So that's a Greek letter there. Looks like a V. I stole that picture from Wikipedia. No point in making my own. They had a very lovely one right there in Wikipedia for me. So those are some different F distributions. The p-values for the F test at ANOVA are the tail area quantities that will be calculated for you. So of course we're going to use software packages to compute our ANOVA p-values. I've given two different outputs here, one from Minitab and one from R. So notice the similarities and the differences in our output. So the Anova table from Minitab, which is this top one, has your factor, error, and total. And it has our S and our R squared and some things that we are familiar from regression. And then it's got these multiple comparison output levels. We aren't going to be talking about this right now, but we're going to mention that you should actually look at it later. And then when we look at the R output, you can see how to put it in. So I've given you the code. The AOV function is the default ANOVA function in R. And it just gives you two rows, one called diet and one called residuals. So now let's look at the similarities and differences in these two versions of the output. So you've got your factor and your error and your total up here in the Minitab output, and in the bottom you have diet and residuals. So diet is your treatment groups, right? That equates to factor up here in the Minitab output. So remember the degrees of freedom for the between groups variation was the number of treatment groups minus 1, and we had 3 diets here, and so our degrees of freedom are 2. So this is your number of treatment groups minus 1. And in our case, it was 3 minus 1 because we had 3 diets. Error in the Minitab output is called residuals in the R output. So many different software packages either call the residuals error or residuals. And so here, notice that we have a total of 12 observations. We had 5 plus 4, which is 9, plus 3, which is 12. And then the degrees of freedom for that error for the within group variation is the total sample size minus the number of treatment groups. So it's n dot minus the number of treatment groups, which in our case is 12 minus 3, which gives us 9. All right, so those two rows are equal. And then Minitab gives you an additional row called total. The total is the total sum of squares and the total degrees of freedom. Notice that your factor and your error, or your between and your within degrees of freedom, add to your total degrees of freedom. And it should always be that way. So this one's between and this one's within. All right, so then we can look at the sums of squares. So we know which rows go with each other in this output. The sum square for factor or diet, or what we call between, is 36. And the sum square for error or residual, which we called within, that natural error variation, is 210. Now what did we say a mean square was? So we've got a mean square of 18 for the between group, factor or diet, which is attributable to the treatments. How do we arrive at that number? Well, remember, a mean square is a sum square divided by its degrees of freedom. So that mean square, 18, is the sum squared for that row, 36, divided by its degrees of freedom, 2. And same with 23.3 for the within group variation. That's 210 divided by 9. So now you can get any of those numbers. If I blank them out on the test, you could fill them in. And then how do we get our F statistic? Well, remember we said the F statistic was the mean squared between divided by the mean squared within. So then, to calculate that, you just take this top mean square divided by the bottom mean square. In either case, we always put the mean square between on top in output and the mean squared within on the bottom. And then we let R, or Minitab, calculate the p-value for us. All right, so we've got the heart of the output understood, hopefully. And so now we're going to conduct an ANOVA for the lamb data. So how do we conduct our hypothesis test? Well, first we state our alpha level. So we're going to assume that it's 0.05. Step 2 is stating your hypotheses. The null hypothesis is that the mean weight gain for diet 1 is the same as the mean weight gain for diet 2, which is the same for diet 3. And the alternative is that at least one is different. Step 3 is stating your test statistic. So here, our test statistic is our F statistic, so it's 0.771. And our p-value is 0.491, which is really big. So the p is not low, the null is not going to go. And of course, if our p is bigger than our alpha, I already did that, we're going to fail to reject the null hypothesis. And step 6 is stating our conclusion. So since we did not find significant evidence for the alternative, we're going to say there is not significant evidence at the 5% level to conclude the alternative. Mean weight gain in lambs after 2 weeks is different for these 3 diets. All right, so that's the Anova test. So What happens with the ANOVA is, if you fail to reject, then you didn't find any significant differences anywhere between the means. And you can imagine from our scatter plot that we began with, it doesn't look like there's a significant difference. It looks like diet 2 might be shifted up slightly from diet 1 and diet 3, but our hypothesis test did not detect that difference. So when you fail to reject in the ANOVA, you kind of conclude that there's really nothing else to look at. If you do reject in the ANOVA, then you want to find out where the differences are. And that is the topic of multiple comparisons. And that's that a little bit of the additional output that Minitab gave you, looking at the pairwise differences. But you should read in your textbook or look at another resource to find out the theory on multiple comparisons. We don't have time to cover it this semester, but I at least wanted to point out that it's there, and that's what you should look at. And there is some theory and best practices to use when you're doing multiple comparisons. All right, so some final notes on ANOVA. It assumes a common standard deviation for the population. So there is an assumption that the variability is the same across, in our example, across the 3 diets. Notice that the mean squared within, which is the mean squared for error, MSE, is a pooled or weighted or average variance for the groups. We view this mean square error as an estimate of the population common variance across the treatments. And then the estimate of the common population standard deviation is the square root of it. So we often call that root MSE, root mean squared error. So if that's a population variance, then the standard deviation is the square root of it. And so lots of software packages call that root MSE. And that's how it's often referred. We check the assumption that the variation is the same for all groups before carrying out an ANOVA, possibly by looking at side-by-side box plots, among other ways. There are other assumptions and methods of checking them, which we were supposed to discuss in the regression and correlation lecture notes. And so what do you do if the Anova test rejects the null hypothesis and we conclude there's at least one population mean that's different? Then we turn to that method under the blanket of topics called multiple comparisons. So healthy study is given to that set of theories. Careful attention has to be paid to the error rates, and 11.9 in your textbook gives you an introduction to this topic. All right, so that's all we know about we're going to learn about the ANOVA for this semester. If you need to do a two-way ANOVA, there are other things to consider, and I encourage you to come to our statistical consulting lab for help, or you can always come and see me.